Okay, the first of these exam questions is about hydrogen bonding. They have drawn one water molecule for you, and then they've asked you to draw a second water molecule and then show how hydrogen bonds form between the two. Okay, in the mark scheme, it said that the most commonly lost marked was when students were drawing their dipoles, they drew the dipole on one molecule and they didn't draw it on the other. Okay, so notice here that I've got my delta negative and delta positive on both molecules. That's really important if you're going to pick up that mark, okay? It's not necessary to have that delta positive, the second delta positive hydrogen, but you need to have at least one delta negative oxygen and one delta positive hydrogen on each molecule, not just on one of them, okay? For your second mark, you need to have drawn in your lone pair, and you need to show that that hydrogen bond is forming between a delta positive on one hydrogen and the lone pair on the oxygen of the other molecule. You also need to do something to distinguish that hydrogen bond from the covalent bond. So I've used a dash line and I've also labeled it as a hydrogen bond. Okay, so something to distinguish it from the covalent bond. Either use a different color or a dash instead of a solid line, or the most common thing is just to label it. The other thing to make sure of is that your bond actually starts at the hydrogen and it ends at the lone pair. It shouldn't just be pointing at the oxygen, it has to specifically point to the lone pair on the oxygen, or you're going to lose a mark. The next question was on the anomalous properties of ice caused by hydrogen bonding. According to the mark scheme, this was really poorly answered. Okay, it said that the first part was okay. So one of the properties is that ice is less dense than water. So that's you stating the property. You'd have to explain that property. So why is that ice less dense than water? And the reason is because molecules in ice are held in an open lattice by the hydrogen bonds. Okay, so open lattice or open structure, or molecules in ice are held far apart by those hydrogen bonds. Okay, and that will get you 2 marks. For the second part, okay, you have to say that ice has a relatively high melting point. And this is where a lot of students fell down according to the mark scheme. Okay, first thing, you're talking about ice, so you're not talking about it boiling, you are talking about it melting. If you said boiling point, you're not going to get the mark. It has to be melting point. The other thing is this word relatively. Okay, ice melts at 0 degrees Celsius. That is not a high melting point. But compared to other molecules of a similar size, ice does have a high melting point. So it is a high melting point compared to other molecules of a similar size. Therefore, we can say it has a relatively high melting point, or an unusually high melting point, or a higher melting point than other molecules of a similar size. But without that word, you're not going to get a mark. You then need to explain why. And again, that word relatively in my second sentence is going to be really important. Okay, hydrogen bonds are relatively strong. Okay, hydrogen bonds are intermolecular forces. They are not strong, but they are relatively strong compared to other intermolecular forces. So I've said hydrogen bonds are relatively strong and therefore require more energy to overcome than induced or permanent dipole-dipole interactions. Okay, but make sure you're practicing a good exam technique on that question. It comes up all the time. There's no reason it should have been so poorly answered. The next question is a 5-mark question, okay? And you're given 3 different molecules, ammonia, fluorine, and bromine, and you're given their boiling points, okay? First thing to note is which one has the highest boiling point, okay? That's quite easy to spot. Bromine has a boiling point of 59. When comparing ammonia and fluorine, okay, remember that minus 188 is obviously colder than minus 33, so fluorine has the lowest boiling point. And the first thing I did for myself before I started writing an answer was just to jot down a few things in the table. So these are all molecules, so they are all held together by intermolecular forces. Fluorine and bromine only have London forces between them, or induced dipole-dipole. Okay, they're not polar molecules, they don't have permanent dipole, they don't have hydrogens, they don't have hydrogen bonds. They've only got London forces between them. Ammonia, on the other hand, has London forces, because all molecules do. It's also got permanent dipole-dipole, and it's got hydrogen bonds. Just jot down the intermolecular force that each molecules have, and then I've told myself that fluorine has the lowest boiling point and bromine has the highest. Then I need to structure this into an answer, okay? So I need to use appropriate technical terms and I need to spell them correctly. So the first thing I'm going to specify is just that ammonia, fluorine, and bromine are all simple molecules. Often in these questions, they'll throw an ionic compound in there as well. So it's really important to specify that they're all simple molecules. You're getting a mark for just saying that they're molecules. Because they're all molecules, if I want to boil them, then the forces that I am breaking are the intermolecular forces. So to boil them, the forces between their molecules must be overcome. The intermolecular forces must be overcome. So I'm specifying their molecules, and I'm specifying that the forces I'm breaking are intermolecular forces. I'm not breaking covalent bonds. That picks you up a mark. It's just specifying that. You also get then a mark for specifying what intermolecular forces you're breaking in each case. So I've said for fluorine and bromine, they both have London forces, while ammonia has got London permanent and hydrogen bonds. So these 2 bullet points that I've written here, that's 3 of my marks. 1 mark for saying that they're molecules, and that I'm overcoming intermolecular forces, and then the other 2 marks for specifying what intermolecular forces they have. London for fluorine and bromine, and then all 3 for ammonia. My last 2 marks then come from making comparisons. I can see that bromine has the highest boiling point. Why does bromine have a higher boiling point than fluorine when they both only have London forces? So I'm going to write bromine has more electrons than fluorine, therefore bromine has more electrons than fluorine, therefore the London forces are stronger. They both only have London, but bromine's London are stronger because it's got more electrons, therefore that will require more energy to overcome. Okay, I now need a last point to compare ammonia with my fluorine and bromine. Okay, I know ammonia has hydrogen bonds, therefore that will explain why ammonia has a higher boiling point than fluorine. So I'm saying ammonia has hydrogen bonds, they are stronger than the London forces in fluorine. That's why it's got a higher boiling point. Okay, but when I look back at my numbers, I can see that bromine has a higher boiling point than ammonia. So despite ammonia's permanent dipole-dipole and despite ammonia's hydrogen bonds, bromine still has the highest boiling point. That tells me that the hydrogen bonds in ammonia are weaker than the London forces in bromine. Okay, so you're given that data, that you just need to make your answer fit the data. So you wouldn't be expected to know offhand that the ammonia hydrogen bonds are weaker than the bromine London forces, but when you're given the data, you need to be able to write an answer that explains it. In question 3, similar to question 1, they've drawn sulfuric acid for you. You need to draw a separate molecule of sulfuric acid and show the hydrogen bonds in between. Now, I've been very thorough. I've included every dipole that I possibly can. On the mark scheme, you're only required to include 1 dipole, okay, on the OH, okay, which I have done in all 4 positions. And then you also need to include your lone pairs on your double bonded oxygens. But to be thorough, I've also included them on the oxygen of the OH. Okay, just fill them in everywhere. You're not going to lose marks for it. And then I'm showing a hydrogen bond between the delta positive hydrogen of one molecule and the oxygen lone pair of the other molecule. Okay, I've shown 2 hydrogen bonds here. On the mark scheme, that wasn't required. You would have gotten a mark for only showing 1 hydrogen bond. But please make sure that your hydrogen bond started at the hydrogen and ended at the lone pair, not just at the oxygen. It needs to end at the lone pair. You're comparing hydrogen bromide and hydrogen iodide. The reason hydrogen iodide has the higher boiling point is because iodine has more electrons. It's got more electrons, therefore its induced dipole-dipole or London forces are stronger. So your answer is going to be D. Okay. On the next one, you're asked why H2S is a lower boiling point than H2O. Okay, H2S is a lower boiling point because it doesn't have hydrogen bonds. That gets you 1 mark, but then you need to specify that hydrogen bonds are relatively, again, I'm using that word, relatively strong, so more energy is required to overcome them. I'm then comparing H2S with H2SE. There are no hydrogen bonds present in either of these 2 molecules, but what I can say is that H2S has weaker London forces than H2SE, and the reason it's got weaker London forces is because it's got fewer electrons. Okay, you could write the converse, say H2SE has a higher boiling point because H2SE has more electrons, therefore stronger London forces. You're then asked to use this graph to predict the boiling point of polonium, which they tell you has an atomic number of 211. So what I've done is I've just gone over to where kind of 211 will be on the x-axis, and I have continued on this line. Now, you don't know how steeply this line is going to go up, but all you can do is kind of look at the original line, and then I just kind of continued it on. And where my 2 points were meeting, I came across to the y-axis and I got an answer of 315. Now, everyone's going to draw their line slightly differently, but luckily on the mark scheme, there's a range of 285 to 335. So anywhere within this range, you will get your mark. So just continue your line on as far as 211, which is the relative molecular mass of H2PO, and then find out where your graph is going to cut your y-axis, and that will give you an answer. Which contains hydrogen bonding. Don't be put off by liquid state. Okay, it's going to be the same in any state. You need to find a hydrogen bonded to either an oxygen, a nitrogen, or a fluorine. The only one where the hydrogen is directly bonded to one of those atoms is in D. The hydrogen is directly bonded to the oxygen, so your answer is going to be D. In all of the other cases, yes, you've got an oxygen here, but it's not directly bonded to a hydrogen. This fluorine is not actually, I know that's a little bit misleading, but that fluorine is not actually bonded to the hydrogen. That fluorine is bonded to the carbon, which is also bonded to the hydrogen. That one's a little misleading, but your answer is going to be D. D is crystal clear, so just pick D. 7, you're asked to compare them both, okay? You're asked for the type of structure. All they want with type of structure is tell me that SO2 is a simple molecule, okay, covalently bonded, and then MgO, you've got a metal and a non-metal, it's going to be giant ionic. So there are your 2 marks for structure. Then you're going to just tell me that the ionic bonds in magnesium oxide are much stronger than the intermolecular forces in SO2. Now, I haven't specified which intermolecular forces I have, okay? You can if you want. So you could mention permanent dipole-dipole, you could mention induced dipole-dipole or London forces, but you should not be mentioning hydrogen bonds if you're talking specifically about the intermolecular forces in SO2. That will get you your 3rd mark, and then you just need to specify that ionic bonds are, because they're stronger, they will require more energy to overcome, and therefore you're going to have a higher melting point when you've got ionic bonds to overcome rather than just intermolecular forces. The last question, you have got P4 and you've got Cl2. You can see from the graph that there's not a huge amount in it, but P4 does have a higher melting point. Higher melting point than Cl2. You need to explain why. Okay, P4, Cl2, they're both non-polar molecules, so the only intermolecular force you're going to have present are London forces, and you need to explain then why P4 would have stronger London forces than Cl2. So I'm going to say P4 has more electrons than Cl2, therefore its London forces are stronger. Those London forces are existing between your P4 molecules. Therefore, because the London forces are stronger, more energy is going to be required to overcome London forces between the P4 molecules and the Cl2 molecules. Okay, when answering all of these questions, when you talk about melting points and boiling points, you'll see so often on the mark scheme that you get a mark specifically for just mentioning energy. So you've already said that they've shown you that the boiling point is higher. You've said that the intermolecular forces are stronger. You then need to say that more energy is required to break those forces because they are stronger in order to get your full marks. And that is the end of those questions.